Here we're going to have a look at fundamental problem 8-9. It's got these two blocks here resting on the floor, and you've got this applied force P. Okay, so you've got block B, you've got block A. Block B is 10 kilograms and block A is 7 kilograms. All right, you've got these dimensions, 300 millimeters, 400 millimeter height, and you've got two coefficients of static friction, mu between B and A of 0.3 and mu between the block A and the floor of 0.1. Now the question is, the reason I chose this question is it's just a lovely question. That's why I chose it. Is determine the largest force P which can be applied to the cord without causing motion. What is the largest force I can apply to this cord without causing motion of this system? Okay, so it's a nice complicated problem, but actually not so complicated. You've got block B, block A. If I apply a force P, what is the largest force I can apply without causing motion? Okay, so let's have a look at this. So you've got B here, you've got A, right? It's resting on the floor, and you've got this applied force P. Okay, now why did I choose this question? Because it allows us to do a couple of things. It allows us to test our understanding of impending motion at some points, and it also allows us to test the idea of slipping and tipping. Okay, so what are all the possible things that could happen to this setup, right, with this force P and these two blocks? Well, the one thing that could happen, remember it says causing motion. What is the largest force of P we can apply without causing motion? So what are the types of motion that we've seen so far? Well, the one is sliding or slipping, and the other one is tipping. Okay, so what are the things that can happen? Well, the one thing that can happen is B can slide on A and A can be stationary. Okay, that's one idea, is that B just, we apply the force P and B slides on A. Okay, another idea is, or another possibility is that B could tip on A. That's also motion. So there's the second one. And the third one is B and A move together, and this whole system slides between A and the floor. Okay, that means that this acts as one. So if I apply B, B does not move relative to A, but this whole thing moves relative to the floor, which essentially means A moves relative to the floor. So we've got these three cases. Let's consider case 1. B slides on A. Okay, that's case 1. So what's the first thing that we always do? Well, we draw our free body diagram. Okay, so we've got our force P, we've got the weight of B, and we've got our normal force, and we've got our friction force at B. So B slides on A. What does that mean? It means impending motion at B. All right, so again, if we draw that graph, it means we're at that point, at point B there, but we're not at that point over there. So we have impending motion at some points. Okay, that's essentially what we're testing here. Okay, so we set up our free body diagram. Then we set up our equations of equilibrium. Sum of the forces in the x equals 0. Sum of the forces in the y equals 0. I'm not going to worry about some of the moments about some point, because we're not testing tipping. We are assuming that this block B is going to slide on A. So we are here, we are at impending motion before we're at tipping. Okay, so what do we have here? Sum of the forces in the x, we have P minus FB is equal to 0. P minus the frictional force is equal to 0. And some of the forces in the Y, okay, actually that NB in reality is being applied somewhere to that side, okay? So if you noticed it, well done. It should be somewhere to the off of center. So we've got NB minus weight is equal to 0. And like I said, I'm not worried about the moment because we're considering sliding and not tipping. So because we're there, what did we say when we are at that point? We can use our equilibrium equations plus our friction equation. So FB is equal to mu B times NB. So that is what we have there. So P is equal to FB. But what is FB? It's equal to 0,3 times the normal force. The normal force is just simply the weight of block B, which is the weight is 10 kilograms times 9,81. 10 times 9,81. And that gives us, let's see, 29,43 Newton. Okay? So FB, so the applied force P is equal to FB is equal to 29,43. So what that tells us is that if I apply a force of 29,43, I'm going to have B sliding on A. Okay? So remember this idea of impending motion at some points. We make assumptions of different cases and then we find out what is our applied force in each case and we compare those. Okay? So what is the second case that we can come up with? Case 2. Let's look at B tipping on A. B tipping on A. Let's draw a free body diagram. What does it mean when we have tipping? It means there's no sliding, which means essentially there's no impending motion of B sliding on A, right? So we have the weight of B. And what is the assumption when we have tipping? Well, that normal force moves all the way to the corner because it is trying to counteract the applied moment due to P. So we've got this H, we've got X here. So when we're considering tipping, we don't have to be concerned about the sum of the force in the X, sum of the force in the Y. We go straight to our moments. Let's call that A. Sum of the moments about A equals 0. And we say counterclockwise is positive. So we have minus PH plus NB times X gives us 0. Okay? So this NB times X is counteracting the applied moment due to P. Sorry, this is just, I don't know why it's not focusing. Okay, there we go, that's better. All right. So, okay, I hope you're still with me. We are now assuming that B is tipping on A, which means that NB can't move any further to counteract the moment, so it's tipping, okay? So we're trying to solve for P. So we have P, what is H? H, I think, was 0.4, if I'm not mistaken. NB is 98,1. That's the normal force given by the mass of 10 kilograms times gravity. And X is the maximum. So what is our assumption? X here is max. X is maximum. And this width here was 0.3 total width, and I think that's 0.15. Let me have a look. Yes. So this has to now be 0.15 when you take moments, and we solve for P, okay? And we have 98,1 times 0.15 divided by 0.4. We get 36,78 Newton. So in order for us to have tipping, we need a force of 36,78, which is higher than the force to cause that to slide. Okay? So purely with regards to B on top of A, it will slip before it will tip, okay? Because it has reached that point there before the normal force has reached the corner. And then the third one is A plus B sliding. Okay, that is the third assumption or third case. Say case 3. Case 3, A and B sliding. That means impending motion at a interaction between A and the floor. Okay? So here then we've got the total system. There's B and there's A. And we still draw our free body diagram. There's our applied force B. And the total weight here will be A plus B. And the total normal force will be A plus B. And we also have our frictional force at A. All right, so because we're looking at sliding, we know, or we're assuming that we are here, we are at the limiting static frictional force, which is Fs equals mu Sn. That's happening here. So we take sum of the forces in the x equals 0. P minus Fa is 0. Sum of the forces in the y equals 0. Normal force of A and B is equal to the weight A plus B, which is just simply equal to 10 plus 7 times 9,81. 17 times 9,81 gives us 166,77 Newton. That's our normal force there. And we know that P is equal to the frictional force, but that frictional force is at impending motion, so we can use mu A n, A plus B. Okay, we can use the limiting static frictional equation. So Fa is equal to 0.1 times 166,77, which is equal to 16,7 Newton. And we know that the applied force P is equal to that. So perhaps that was counterintuitive, but what's actually happening is, in order to get this total system moving at the floor, between this block and the floor, we need a force of 16,7, which is much lower than the force of 29,43 and the force of 36,78. All right? So what's going to happen first is this whole system is going to slide at the floor before B slides on A and before B tips. Okay? So I hope that helped. I hope it was interesting. I hope you learned something. Cheers.